Good afternoon. I'm Michelle Sanner, and today we are going to be talking about two different topics: units of measurement, what they are and why we use them, and scientific notation, just as a review. So, our learning target today is twofold: be able to use the correct unit of measurement for a given task and be able to express that unit of measurement in scientific notation as need be. So, why do we measure? Well, chemistry is, by its own definition, the science of matter and the way it interacts. And unlike the life sciences and biology, chemistry is the science of precise measurement. So, it's not enough to take a measurement, but we also have a level of precision, a level of accuracy that we seek to achieve with our measurement. Every quantity in the universe that has matter, that has mass, that has volume, every quantity has a unit. Even things that you count up around the house, number of slices of bread. Well, the unit is slices of bread. Your weight is expressed in a unit. Distance is expressed in units. Numbers have no meaning unless they are used to describe a phenomenon, or in our case, a measurement. And what's interesting about units is that they're actually arbitrary values. Someone has chosen that a foot is a foot or a kilometer is a kilometer. And even although they are arbitrary, they're also fixed in that they are standardized and the same from case to case to case, so that a foot is always 12 inches, no more, no less. And these arbitrary values measure certain characteristics. Let me give you an example. I am 5'4". That means 5 feet and 4 inches tall. But I'm also 1.65 meters tall. These are two true statements. They're just using different units to represent an actual phenomenon of height, in my case. The value of my height does not change. Only the number and the unit that I am expressing it in changes. So why do we measure? Again, a measurement without a corresponding unit is meaningless. I often say no naked numbers in chemistry, because if you were to put your answer, say it's 2.3, that answer is automatically wrong, because what are you talking about? 2.3 laptops, 2.3 feathers, 2.3 elephants? A number without a unit has no meaning. So you need to always include whatever unit it is that you're measuring. Let's say, for example, it's grams, or your answer will be wrong, even if you're numerically correct. So get in the habit of not only including a number, but also a unit as well with every measurement that you report. So we have a couple of different types of units. These are the SI units, or, and I don't speak French, Système International de Unit, and these are the base units for all possible measurements. The four that we're going to focus on this year are mass, which has the base unit of kilogram, and the abbreviation of lowercase k, lowercase g. Be careful, because upper and lowercase mean two different things. They matter. So a little k stands for the prefix kilo, whereas a big K, like down here, stands for an entirely different form of measurement, measuring temperature in units of Kelvin. So mass is base unit is kilogram, abbreviation is lowercase k, lowercase g. Length is measured by the base unit of meters, which is identified by the abbreviation lowercase m. Again, the case matters here if you're upper or lowercase. Time, it has the base unit of seconds, and temperature has the base unit of Kelvin. So I'm going to stop and talk about each of these in a moment here. But take a second and jot down the measurement, the base unit, and the abbreviation. Pause the video if you need to. Let's start by talking about mass. Mass is defined as the amount of a given substance. Now, it's different from weight, because weight is related to the gravitational pull enacted on a body by a planet, like the one that we're on right now. My mass, if I were to go on Mars, would still be the same. But because of the difference in size of our two planets, the Earth and Mars, my weight would be slightly different. So mass is intrinsic. Mass does not change. Mass is a measurement of the amount of a substance. Weight can vary from planet to planet. So we tend to kind of get lazy with our language in chemistry. We may say, oh, go weigh out that sample for me. But really what we should be saying is take the sample's mass, or mass the sample. because it's not weight that we care about here in chemistry. It's actually mass, the amount of a substance. Looking ahead, we look at temperature. What is temperature? Crazy enough, all temperature is a measurement of the average kinetic energy, or that is to say, the speed that particles are moving. So in a substance like, say, water, if I took the temperature of water at boiling, it would be 100 degrees Celsius, which is to say it has a certain kinetic speed. It's moving pretty darn fast, and when it's boiling. Fahrenheit and Celsius, two scales that you might have heard of. We've got Fahrenheit here in the US, degrees Celsius literally everywhere else in the world. They're both derivative units of Kelvin. So our Kelvin scale is the base unit because it has no negative numbers. The Kelvin scale goes from 0 on up because theoretically at 0, which is particle movement, remember, temperature is a measurement of average kinetic energy. Theoretically, at this 0 Kelvin temperature, there's no movement. There's 0 movement. We call this absolute zero, maybe you've heard of it, and you can't really have non-movement. Non-movement is just no movement. So the lowest you could possibly get in terms of temperature would be 0 Kelvin. Now in Celsius, which is a slightly different scale, you can actually have negative and positive numbers in degrees Celsius. Same thing with Fahrenheit. And that's why Kelvin is our base unit. Celsius is, of course, based on the freezing point of water, 0 being the point at which water transitions between a solid and a liquid, and 100 degrees Celsius, the point at which liquid water turns into a gas. Now, volume is another unit that we might use. Volume's base unit is liter. And a liter is given the prefix or the abbreviation of a capital L. Volume is a derivation of length. That is to say, volume is a three-dimensional representation of length. Imagine you have a cube. And this is about as good as my drawing skills get. And this cube has a side of 1 centimeter. It has a depth of 1 centimeter. And it has a height of 1 centimeter. It's a 1 by 1 by 1 cube. This is also called a cubic centimeter, centimeter cubed. It's also known as a cc, cubic centimeter, in medical settings. It's also the same as 1 milliliter of a substance. And that's important to remember because we often will be transitioning between centimeters and milliliters. We need to be able to understand how something like length is actually related to volume. So there's a nice little ratio for you. 1 centimeter cubed corresponds to 1 milliliter. Now, a liter of a substance, if we were to break out what that looks like, it would actually be a cube with 1 decimeter side, 1 decimeter depth, and 1 decimeter height would correspond to a liter of a solution. So each base unit can have a common multiplier applied to it. What I mean is we can put a prefix in front of any base unit, and no matter what that unit is, that prefix is going to apply the same value, the same multiplier value to that base unit. Let me give an example. The base unit of kilo means 1,000 of something. So 1 kilometer, or we say kilometer, corresponds to 1,000 of that base unit meter. 1 kilogram corresponds to 1,000, again, of that base unit of grams. We can go on and on with any other. 1 kiloliter is 1,000 liters. 1 kilobyte is 1,000 bytes. And here's another really helpful one. This kilo is one we're going to use all the time. Milli as well. Milli is another unit prefix that when applied to a base unit, like in this example, meter, tells you a little bit about the multiplier. A millimeter, as you can imagine, a little small, about the width of my fingernail, the thickness of my fingernail. That's a really, really small amount. And there's 1,000 of those in a meter. Another way we can say that is it's 1,000th of a meter, 1/1000th of a meter. And then using that same prefix, a milli, we can look at it according to a different base unit, in this case, gram. It still means the same thing. Milli still means 1,000th or 0.001 of that base unit grams. We also have some crazy units out there like tera. Tera is a huge multiplier. The prefix tera means 1 times 10 to the 12 of something. In this case, your 1 terabyte hard drive, it actually means 1 times 10 to the 12 bytes of data. We can have nanometers. These is a really, really small multiplier. So the prefix nano means 1 times 10 to the negative 9. So that's 0.0000, well, 8 zeros. Push the decimal place 8 zeros. And that's how many meters it is. Really, really small meters. And in fact, this nanometer range is where we kind of start our chemistry studies in. We're talking small. We're talking in the nanometers and even below that, picometers, things like that. So here is a chart from your book. You don't need to write it down, but here's the citation right up here in case you want to know how to find it. These are all the different prefixes you may be asked to convert between. Why would we want to convert? Well, maybe it's not very convenient to write out 12 zeros. Maybe we need to convert that into something a little bit more manageable, a little bit more easy to write on a piece of paper or on a word problem. And so we're going to use scientific notation and these unit prefixes in order to convert between different units of measurement. Certainly, you need to commit kilo and milli to memory. These are ones that you should be able to know off the top of your head. I also think that centi is one that you should be very familiar with at this point. So because these units are metric, and because they can be very, very large, very, very small numbers, it's important that we review scientific notation. In scientific notation, you'll have a number written in the form m times 10 to the nth power. And m is usually some number, 1.2, or maybe it's like 3.41 or something. But it's a number greater than 1 and less than 10. So we never go above 10. We never have more than, we never have a 10th place, a tens place. We only go with the ones place and then maybe a 10th place and maybe a 100th place. N here, the exponent, is a whole number, but it can be a positive whole number or it could be a negative whole number. Positive whole numbers correspond to really, really large values. Negative whole numbers correspond to small values, values that are smaller or a fraction of the base unit. So why do we do it? Well, it's a way of writing very, very large and very, very small numbers without having to add a bazillion zeros, which starts to become quite cumbersome. There's a common issue that I've noticed in my years of teaching students. It has to do with the fact that we all have different calculators. I don't care what calculator you use this year. I just want you to decide on one and be consistent with it. So how would you type this scientific notation into the calculator? 1.2 times 10 to the third. Now, many students would simply write out, 1.2 times 10, and then maybe they use the little third button. Maybe they use the little caret 3. Now, this is usually incorrect. Almost 9 times out of 10, this calculator will not process this scientific notation correctly because the calculator will go and it will take the 1.2 and it'll go times 10. It'll do that first and then it'll stop. Then it will take everything all together and raise it to the third. That's not what we're trying to get it to do. Instead, I want you to find on your calculator an uppercase E. It might look like a button with just an uppercase E. It might look like a button with an uppercase, 2 uppercase E. And I have one calculator that goes like this, times 10 to the. So we'll spend some time in class actually going through and figuring out what is the right button for you. And I hate to break it to you, but the old, please excuse my dear Aunt Sally, PEMDAS, it doesn't really work in calculator world. It's kind of untrue. You were taught to first do parentheses, then exponent, then multiply and divide. I have news for you. The calculator treats multiplication and division with the same weight. So it doesn't always multiply first or always divide first. Usually it just goes left to right across your calculator screen. So it's important that we articulate to the calculator when it needs to multiply and when it needs to divide. And we're not going to just trust it to do it for us. So whatever calculator you decide to use, it's fine with me, as long as it's not something that you have. You could use your phone calculator. You won't be able to use that on a test most likely. So I would suggest that perhaps you use the Google Chrome calculator. Nice free browser-based calculator. You literally just type in scientific calculator into Google and it'll pop one up for you. No need to go and buy one. So it's important, again, Very, very important today to determine what calculator you're going to be using for this year and become familiar with its buttons. Also, one other little word of warning. Uppercase and lowercase e mean two completely different things. So don't interchange them when you're doing calculator operations. Okay, the next time we meet, we're going to actually start to do some of these scientific notation practice problems, converting in and out of scientific notation. And we're going to spend some time converting in and out of different unit prefixes. So I hope you're doing well and you're having a great day, and I'll see you soon.